principle. In fact, Fermi-Dirac distribution applied to all fermions, right? All fermions. There are I think six fermions in the universe, right? Leptons, the lepton is the fermions, and the electron is the fermion. They're fundamental particles, so they have unique property. And one of the unique properties are these, right? They have to follow Fermi-Dirac statistic and Fermi-Dirac distribution. And what does it mean in real terms? It just means that when you feel this energy state of these fermions, you have to, the population F of E, depending on energy, has to follow this formula in this way. 1 over 1 plus e to the minus EF divided by kT. Right? So you notice both of these, the temperature is starting to come into play. It is temperature dependent. And you can approximate, if depending on this term is very big, you can drop the 1 as simply proportional to e to the minus bracket e minus EF divided by kT. So it's very similar to this, right? It's very similar to the Boltzmann distribution in many ways, the Fermi-Dirac distribution, other than this introduction of this EF. This is, of course, the so-called Fermi energy. What is the Fermi energy? Okay, so the Fermi energy is a unique point in this distribution. Is that when E, your energy, is equal to the Fermi energy, this term, right? This term becomes 1. Okay. So what does it mean? It means that if you are starting to feel your particle, right? Particle, either electron or atom into your space. Then what happens that you will get, right? If this is 0 divided by when E equal to EF, the top term becomes 0. Okay, and then it's a tricky point because you have E to 0, and it will depends on what this T is doing. If T also go to 0, then you have a step function. You have a sort of imagined point like this. You have a step function. If you plot this distribution, you usually have a curve like this. Okay, and it depends on the temperature. So here, for example, I plot this F function as a function of temperature, as a function of Fermi energy. Right, as the energy at this point. So this is my energy, and this is my 0. This is actually E minus EF. So if I would change my scale, this would have been EF. Right. So if I replot my scale in terms of energy, then this becomes EF. Right. So as I approach EF, you will get a step function. You get a distribution like this. Okay. And this step function changes with temperature. This step function, so if you go a high temperature, you see this spreading of this probability of filling these states. So these are number density, right? This is distribution, meaning number density, the population of your electron at that particular energy. So here you have population at one energy, population at another energy, and so forth, all at the same temperature, 700K. And so the distribution, so this is called distribution, how the curve shape changes as a function of energy, or energy difference from the Fermi level in this case. But what you find is that okay, if you do that at 0 Kelvin, right? At 0 Kelvin, you got a step function. So this become in some way infinite slope. So this is an interesting point. It becomes an interesting slope. But of course, nothing have reached. You can never reach absolute 0. Nobody can reach absolute 0. The coldest you can get on this campus is I think 50 millikelvin. So this is done in Yan Kangxi's lab. So you can get it coldest using helium refrigerator a lot of 50 millikelvin. And that's the coldest on this campus. And you can get colder than that. You can get to even lower microkelvin and so forth. And that involves a lot of lasers power to do laser cooling and stuff like that. Okay, so the Secretary of Energy in the U.S., Stephen Chu, right? Stephen Chu got the Nobel Prize. He's a Nobel Prize winner in physics, and he was awarded the Nobel Prize because of understanding laser cooling. So that's his thing, to do laser cooling, right? So so you need to involve a lot of work to get close to 0 Kelvin. So this distribution, this step function, you never see. What you see is this smooth function. It's still a step, but it's a round-off step with round-off corner like this. Okay, so that's what you get. So as we increase the temperature distribution, is sort of smoothed out, indicating some of the electrons. So you have some step function like this. Some of this electron, so here in the hatchet region, get transferred in the bottom line, above the Fermi edge. So some of the electrons below the Fermi level get moved up to above the Fermi level due to this finite temperature effect that you see. Okay, and so that is kind of interesting because what will happen to it? So the width of this distribution, right? So I try to measure. Let's say I like to estimate how wide is this width. So how will you do that? Okay, so I can make some rule, right? So I can say that, okay, I would define my rule, the width of this band, right, to be, let's say, 90% to 10% of my maximum, something like this. So if this is 100%, then I would say from 90% to 10%, right, I found where this is and this is, so this is 10% of the maximum signal, right? And I'll call this to be my width, right? So you can see at high temperature, if I define some criteria, the width is increasing, right, as I go through. And this total width of distribution from an energy, right, is about, okay, so it really depends on how you define it, but in general it's between, usually people define it 10% to 90%, usually that's the way. You get about 4 kT, right? So it depends, even this width, how much electron get moved up above the Fermi level, from below the Fermi level to above the Fermi level, depends on the temperature. This is around roughly 4 kT. So this is a useful number to think about. So this is in energy, of course, you convert temperature to energy. And so at room temperature, you substitute T to be about 300 K. What you got is about 0.1 eV. Okay, so that's a very good number to remember, right? Because that defines your width of how much thermal excitation you get from the brain. Okay, so 4 kT and 0.1 eV of this kind of distribution that you see. So the way to think about it in chemistry then is that this is all physics way of thinking, but we can think in terms of chemistry, and the way to think about chemistry is that the Fermi level, really Fermi energy can be thought of as a chemical potential that we learned about in thermodynamic classes for electron. So it's a chemical potential for electron is solid. So that means that, so just like any chemical potential, why is it called chemical potential? Is because you put the two chemicals together, either in contact or whatever, the chemical potential will try to equilibrate itself, right? This is how chemistry occurs, is that the material with the higher potential will try to change its chemical potential to become equal to the one, bring its chemical potential down so that it's the same as the one with the lower potential after it brought its own potential up. Okay, so it's just sort of up and down until you get the same. And how do you do that? Well, in chemistry, you do reaction, right? So you have reaction that drive this process so that the chemical potential of your two materials essentially become the same. And And it's the same way here, that here you have, if you put the two solid that you together with different um, Fermi energy, right, which is what we're talking about, then the Fermi energy will try to equilibrate themselves, and so that you would have then electron transfer, right? An electron will then flow from one solid to another, causing the chemical potential to cross the thing to become a potential difference. Once you put the two material with different Fermi energy together, you have a potential difference, and therefore the energy, the electron will flow across this potential difference. Until such time that you change it, equilibrate it to a different chemical potential of the combined material, then the flow of electron will stop. Just very much like chemical potential that